So ideally, the larger block should reduce miss rate. So we have talked about the spatial locality and the temporal locality, remember, in the last class. So what if I increase the block size? Do you think it will help us reduce the miss rate? So instead of having a block size of one word, if I say that the block size is, let's say, 20 words, okay? So when we import the data from the memory, it will be not only it will not be importing one word. Now it will be importing 20 words into the cache. Do you think it can reduce the miss rate? Okay. Yeah, it is actually, because due to spatial locality, the spatial locality says that the data that is recently accessed, the nearby data is likely to be accessed. So it has been observed that if we were to implement this thing, is the block size against the cache size here, and this is the miss rate. So when we increase the block size, the miss penalty increases. But miss penalty may go up eventually if the block size becomes significant larger fraction of the cache size. Why? Yep.
Because at a certain point, the data around it becomes like less relevant because you're not always using these like massive pieces.
Yeah, because the less number of blocks can now be accommodated in the cache. And okay, so let's go at like this. So when block size becomes significant larger portion of the cache size, less number of blocks can be accommodated in cache. The competition among block increases because previously, for example, if we were able to accommodate, let's say, 10 blocks, now we can accommodate only 2 blocks with larger size. So if the data that is requested is not found in the current block, then the entire block has to be replaced, right? It has to be swapped with the other block in the memory, which means that the block bumps out before many of its words are accessed. Okay, so that is why the miss rate appears to increase, and it eventually decreases the spatial locality, and miss rate is increased. So another disadvantage of increasing block size is miss penalty increases. So what is miss penalty? Do you remember I discussed that in the very first lecture? So miss penalty corresponds to the time required to fetch the data block from the main memory and load it into the cache. The time required to read the data from memory and put it in the cache. It is called the miss penalty. So time to fetch the block contains 2 components: the latency to the first word. So for example, if you are fetching the block from the memory which contains 20 words. So fetching the first word and then fetching the rest of the block contributes to the total time or miss penalty. So increase in miss penalty eventually overwhelms the decrease in the miss rate. So because of the time it takes to read the data, because what do you think? Will it be faster? Like if you were to grab a single book from the shelf and bring it into your desk, or let's say 20 books and bring it into your desk. Of course, this later example or later case will be slower. Okay, so same is the case. If you are reading the larger block size, it will take larger amount of time, and hence the miss penalty overwhelms the decrease in the miss rate. So we can hide some of the transfer time by following some strategies. So one of the strategies is called the early restart. So it resumes execution as soon as the requested word for the block is returned. So for example, if we have something like this, so let's say this is the memory and we have the data arranged in these blocks. So suppose this block contains 4 words and we have requested the data, let's say it is 1200, 1204, maybe 1196, 1192. And suppose the processor requests the data placed at this address 1200. Okay, so early restart suggests that it has to actually copy the entire data into the cache. As soon as, so it will transfer word by word. So as soon as this word is transferred here, the processor will resume the execution of the instruction and let the rest of the data copy alongside. Okay, so this is what the early restart strategy suggests. Resume execution as soon as a requested word for the block is returned. But this is only effective for the instruction cache, because the instruction cache, if we assume that the every word is transferred in every clock cycle, then the processor can execute, keep on requesting the word in every clock cycle and keep on executing the instruction without stalling. But it is not effective for the data cache. Why? Why do you think? Look at the same example that I gave in the, on the whiteboard. So for example, if we have two back-to-back LW instructions, so one LW instruction requests data 1200, let's say, so it is delivered to the processor, and the next LW instruction requests data from another block. So if the current transfer of the data is not yet completed, and the LW instruction, another LW instruction is requesting another transfer, then it must stall before the previous transaction has been completed. Okay? More effective approach is the critical word first. So in the previous example, so we started fetching the data word by word, and the 1200, as soon as the 1200 is fetched, it resumed the processor resumed the execution. Here the critical word first means whatever is requested, transfer it first, and then transfer the remaining part of the block. But again, it is not helpful for the data cache if you are requesting data from the cache.